Hello dear students, welcome to Pen and Paper Chemistry. We are continuing with our topic of the properties of haloarenes, and this is part 2 of the videos on the series. In the previous lesson, we have already discussed how and why haloarenes are less reactive than haloalkanes towards nucleophilic substitution reactions. We also talked about the ortho, para and meta directing groups. So what are these? The atom or the group already present on the benzene ring decides where and at what position the incoming group will enter into the benzene ring. So if I have any atom or group, that atom or group could be Cl, Br, NO2, SO3H, OH, any atom or group which is already present on the benzene ring decides the position of the new atom or group. So a position just next to it would be called as the ortho position. So we had already spoken about it as the two ortho positions. 2 next to it is the meta position. So there are 2 meta positions here, although the 2 positions are not different. Then we have the para position. So we have Y over here exactly opposite to the atom or group which is already present on the benzene ring. So we have ortho, O-R-T-H-O. Then we have meta and the para, which in short form are written as O, M and P. Why I am stressing on this is because further on you are going to name the compounds with the help of these symbols. We classified the properties of haloarenes into 4 categories. We said electrophilic substitution, the main set of substitution reactions in haloarenes, nucleophilic substitution, reduction and some miscellaneous reactions which are similar to the haloalkanes, but how they are different is what we are going to study under miscellaneous. Further, under electrophilic substitution, I had given you a challenge to write down the reactions for the 5 electrophilic substitution reactions which you will encounter in most of the aromatic compounds. In some you will encounter 3, in some you will encounter 5. Why I am saying that you will know. There are many others, but for your level of knowledge that is required at this level, we are going to focus on these only. So are you ready with your pen and paper? Because I'm going to come up with an easy to remember flow chart for you, which will help you not just to write the reactions now, it will also help you to recall. It will also help you in conversions, which is a tough task for many students, including me. So let's get going with your pen and paper handy. You see over here, haloarenes, electrophilic substitution, and I have expanded what we are going to do. The products are not yet complete. If you notice, all the products are the same. So what I'm going to do in this lesson is, we've got a haloarene and I am taking the example of chlorobenzene. You can also take bromobenzene. Chloro and bromo, their behavior is somewhat similar. When we talk about electrophilic substitution, means the hydrogen of the benzene ring is replaced by an electrophile, an electron loving species. Electro comes from electron and phile means loving. So an electron loving species. When I talk about halogenation, that electrophile is Cl positive or Br positive or I positive. These are the groups which are going to replace the hydrogen on the benzene ring. The halogen atom is ortho-para directing. As I said earlier, in order to clear concepts on this heading, you will have to revise the topic from another video that I have already posted onto the channel. Now, when I talk about halogenation, so let's say another chlorine atom is entering. So it is going to enter, let me put it in another color so that you are able to understand. So it is entering at the ortho position with respect to the previous chlorine atom, and it is entering at the para position, right? So these are your two products. You can name them as 1, 2, 3, 4, 5 and 6. So you can name this as 1,2-dichlorobenzene, right? Similarly, can you name the second one? It's becoming a bit messy, right? So why not go on and write the reactions neatly? So I'm taking the example chlorobenzene and treating it with chlorine or bromine. Now, if you have revised the topic of benzene, then pause the video and write all the conditions of the reaction that you can remember from the topic of benzene. When you do that, it will be a very good revision for you, and at the same time you will start enjoying this subject. Otherwise, you will keep crawling, keep cribbing, and you will never get a hang of it. I am not writing the conditions here. I want you to pause the video, write all the conditions. So write the temperature, write if there are any pressure conditions. I don't know. No, I am not going to tell. And any catalysts which are there for this reaction to take place. So what happens over here? Chlorine, which is already present on the benzene ring, here I will have chlorine at the second position, in which case it becomes 1,2-dichlorobenzene. Yes, I got the spelling right. No, I am correcting it. So benzene. Similarly, the second product is, here again we will have chlorine and the second chlorine atom opposite to it. So I'll have 1, 2, 3 and 4. It's 1,4-dichlorobenzene. From IUPAC nomenclature, we know that we have to write the halogen atom as a prefix, right? Now, out of the two, which will be a major product? As I said earlier, in this case, in the case of para-dichlorobenzene, oh, what word did I use? I used para-dichlorobenzene, right? So where does the para come from? Yes, absolutely. That means there are two chlorine atoms and they are located para to each other. I've drawn this, but if you notice in the flow chart, the structure is shown like this, correct? Are they any different? No, they are both the 6 carbon rings. Every time you have to show the chlorine opposite to each other. That's all you have to do. The chlorine can be at any of the position, but the second chlorine is opposite to each other. And if I am talking about orthodichlorobenzene, that means the two chlorine atoms are on adjacent carbon. Understood the difference when we say para-dichlorobenzene? That means there are two chlorine atoms which are located para to each other. When I'll say orthodichlorobenzene, that means there are two chlorine atoms and present ortho to each other. Although according to the IUPAC system, we should be using numbers, but at many places you will find the name ortho and the para prefixes attached to the name. So, just for your clarification here, I have mentioned both of them. Which of the two would be major product? Which will be formed in a greater amount? Yes, it's the para product. Why? The distance between the two atoms is more. So we say there is less steric hindrance. There is less repulsion between the two. Here what happens is they are closer to each other, so that they wouldn't want to be close to each other when they know that they can have the luxury of a bigger space, right? So can you complete this table now? Let me do away with the numbers over here to avoid confusion, and you will have the first part of your flow chart ready. So we'll have chloro over here and chloro over here. Chloro, chloro. If you want, you can write the names of these. If not, I leave it to you. And here you are going to write the reaction conditions, right? Again, this is a blank to be filled by you. If you can grab hold of some big sheet of paper, like a chart paper, you don't want to spend on a chart paper, get hold of an old calendar which you no longer need. Behind it you will find blank space and sketch pens. That's it you need in order to do this flow chart and stick it to your study space. Wherever you sit and study, be it the dining table, your study table, on a mat, on the floor, just close to that you stick this chart. Observe it day, night for 3 days. And that's it. The reactions become embedded. You don't have to memorize and sit down like a parrot to do it. But what will do the magic is the pen and the paper. You want it to remain in your head. You need to write it down just like I am doing it now. Let's go on to the next reaction, nitration. So how do you carry out nitration? Yes, it was something to do with two concentrated acids. Which one are those? Write it down. So when you're doing nitration, the electrophile over here is NO2 positive, right? An electrophile, electron-loving species itself with a positive charge. So we have NO2 and we have NO2, right? So orthochloronitrobenzene, parachloronitrobenzene, correct? Let's go on to sulfonation. So sulfonation means replacement of the hydrogen by the SO3H group. What will be the condition of this reaction? Somebody is fuming. Yes? Did you get the hint there? Yes, go ahead. Write the reaction conditions over here. Would you like to try and write down the product yourself before I give you the answer? You like it, try it. Pause the video. Try it yourself. You'll really be happy. I just want to see the smile on your face when you understand. Go ahead, try it. There we go. So we will have SO3H group over here and we will have the SO3H. Benzene sulfonic acid will be the parent compound and the chlorine is attached to it as a prefix. So orthochlorobenzene sulfonic acid, parachlorobenzene sulfonic acid. Interesting. Did you like it? You smiled? Yes? I'm so glad to know that. Okay, Friedel-Crafts. Friedel-Crafts. Remember, what's the catalyst? Okay, just don't forget the anhydrous aluminium chloride. And the most important thing, anhydrous seems that it's not so important, but no, don't ignore it. Many of the examiners will not give you marks if you don't write anhydrous. Yes, we examiners are quite ruthless. So anhydrous aluminium chloride, and we are talking about alkylation, that means replacement by an alkyl group. So what is the reagent over here? You could use an alkyl halide, any of the alkyl halide as the reagent, but don't forget the reaction conditions. Can you recall other catalyst other than anhydrous aluminium chloride? Yes, again go back to benzene. Find out the answer. So replacement by the CH3 group, right? Methyl benzene, or you can say toluene. So this becomes the parent compound, which is toluene, and the two groups are present ortho to each other. So orthochlorotoluene. What's the second product? Yes, you did it. Parachlorotoluene. Yes, I'm so happy to see that you are taking so much interest. So what you have to do is, you got chlorine over here and you reacted with an alkyl halide. So let's say I'm talking about CH3Br, one of the catalysts that I already mentioned to you, anhydrous aluminium chloride. There are others as well which we did study. Okay, replacement of the hydrogen by an alkyl group. Replacement of the hydrogen by an alkyl group, but at the para position now, right? So orthochlorotoluene, parachlorotoluene. How do we write it, teacher? You are only saying it. Can you please spell it for us? Yes, dear. There you go. Parachlorotoluene. Which of these will be major? The ortho or the para product? Apply the rule. The further away, the better it is, right? So this will be our major product. Similarly, please go ahead and write the reactions for nitration, sulfonation. Go ahead. Without writing, this lesson is not complete. Friedel-Crafts again. So I have anhydrous AlCl3 as the catalyst. Acylation, that means RCO group, replacement by RCO group. So what can you take? You can take substances like acetyl chloride. So what I'm going to do over here is, I'm going to just write the electrophile, R positive CO, right? Go ahead and connect it. Yes, it will be COCH3. Got it? Same way again, we've got the para product. What's the parent compound over here? There you go. It's acetophenone. Or what you will simply write it as C6H5COCH3. That's acetophenone from acetyl chloride. But what has happened over here is, one of the hydrogen of the benzene ring is replaced by a chlorine. So what does it become? Let's avoid this mess and let's write this reaction properly, shouldn't we? Let's go ahead. So I have chlorobenzene. By the way, if you are looking for the mechanisms of this reaction, they are there as a separate video on the channel under the heading of electrophilic substitution reactions. And they are very much a part of your curriculum. So please make sure that you practice the mechanism as well by writing. So what did I take example over here? For acylation or acetylation, both are the same. So positive here, CO, reaction condition, and we will have here our first product, Cl. Yes, COCH3. Yes, we're going to attach it through the carbon which is positive, right? Did I say R positive earlier? No. I was mistaken. I think while recording I made it, I may have got a little confused. Yes, please. Apologies. Cl, and there we go, COCH3. How did I name it? If there is no chlorine, the common name. Now, why are we taking the common name is because IUPAC system still accepts the common name of some of the aromatic compounds actually. So this is acetophenone, right? Now, if I attach a chlorine to it, Cl, which is ortho to it, so what does it become? So it becomes orthochloroacetophenone. If you are confused about it, please have a look at the IUPAC nomenclature again, which we have already covered on the channel, considering all the major points which will be good for a quick revision. So how will you name this compound? Parachloroacetophenone. Which will be the major product? Perfect. It's the para one which will be major because of steric hindrance, right? Now these are general points that I have taught you. There may be variations if there are other groups or substituents present, or if you bring about slight change in the reaction conditions, okay? But for your level, I think this much of electrophilic substitution is good enough. Now I'm going to talk about an interesting fact. What happens when one of the electrophile has already become attached to the benzene ring? So one is already there, there's another one which comes in. How does it affect the behavior of the benzene ring? Now, because we've got an electrophile, an electron loving group over here. Now, this is electron loving means it will withdraw, it will take up the electron. Come electrons, come towards me. And there is this another group which is, okay, come. I can take away the load of the benzene and share some of the electrons. So that's an electron loving group. What happens to the benzene ring in that instance? Yes, it starts getting deficient in electrons. If it is starting to get deficient in electrons, that means if there is something which is seeking a positive charge, or something which is having an affection or liking for a positive species, what do you call it as? Yes, a nucleophile. A nucleophile comes and takes advantage of this situation. See how bad they are. They're taking away your electron. I have electron, I can give you, right? So it is able to take advantage of the infighting and replace the halogen atom. So what happens is the nucleophile becomes attached over here. But what did we say at the beginning of our lesson? We said that the nucleophilic substitution reactions are difficult. But what do you notice? Because of the presence of these electron withdrawing groups which have entered into the benzene ring, do you notice nucleophilic substitution reactions become a little bit easier? More of this in the next video, where we will be talking about nucleophilic substitution reactions in the case of haloarenes. In the meantime, please make sure that your chart, which chart? This is ready. right? Why? Because I am going to add more to this later on. We are going to extend this further and we are going to talk about nucleophilic substitution reactions, and it will become very, very easy then. So stay connected. Don't forget to practice. See you in the next video.